In the dawn of the 20th century, science stood on the edge of a revelation. The universe that once seemed governed by clear, predictable rules began to reveal a strange and mysterious side. At the center of this mystery was one of the smallest things imaginable, the atom. For centuries, thinkers and scientists had wondered what held matter together. They had broken down substances into smaller and smaller pieces until they reached something fundamental, an indivisible particle, which they called the atom. But as science advanced, the atom was no longer seen as a solid ball. As the ancient Greeks imagined, it became a miniature universe of its own, with a dense nucleus surrounded by swiftly moving electrons. Yet this understanding came with a question that no one could answer. If electrons were negatively charged and the nucleus was positively charged, why didn't the electrons simply spiral into the nucleus? Why didn't atoms collapse and the universe disappear into nothingness? The question may seem simple, but it was the kind of mystery that shook the very foundations of classical physics. According to the physics of the 19th century, anything that moves in a circle must be losing energy, just as a planet orbiting a star experiences gravitational pull, or an object tied to a string whirls around until friction slows it down. When scientists applied these laws to the atom, the results were alarming. If the electron truly moved around the nucleus as the model suggested, it should constantly emit radiation, lose energy, and eventually fall into the nucleus in less than a fraction of a second. That meant matter itself should not exist. Everything solid, every molecule, every structure in the universe should have collapsed long ago. And yet, the world existed. The air we breathe, the light we see, the bodies we inhabit. All of it was made of atoms that somehow defied the logic of the classical world. Something deeper was at work, something hidden beneath the equations of Newton and Maxwell. At the turn of the century, the best minds of science were puzzled. The great British physicist J.J. Thomson had discovered the electron in 1897 and imagined atoms as spheres of positive charge, with electrons embedded inside, like plums in a pudding. This plum pudding model, as it came to be known, was elegant but flawed. Then came Ernest Rutherford, who bombarded thin gold foil with alpha particles and made a stunning discovery. Most of the atom was empty space, with a tiny, dense, positively charged nucleus at its center. This experiment shattered Thomson's model and gave birth to the nuclear atom, but it also deepened the mystery. For if the electrons were indeed orbiting this nucleus like planets around the sun, classical physics declared such an arrangement unstable. The atom should collapse, yet it didn't. Rutherford himself knew something was wrong. He could describe what he saw, but not why it behaved that way. He famously said that his model worked beautifully until you begin to think about it. The reason was simple. According to the laws of electromagnetism, a moving charge radiates energy. An orbiting electron would thus lose energy, spiral inward, and crash into the nucleus almost instantly. The atom, as Rutherford described it, could not survive for even a trillionth of a second. But the atoms in our bodies were not collapsing. The stars were shining steadily. The laws of physics had failed to describe the smallest building blocks of matter. Into this confusion stepped a young Danish physicist named Niels Bohr. Bohr was born in Copenhagen in 1885, and by the time he reached his mid-20s, he had already begun to challenge the established ways of thinking about the universe. What made Bohr different was not just his intelligence, but his philosophical depth. He had a gift for seeing the contradictions in scientific theories and imagining ways to reconcile them. When he studied Rutherford's nuclear atom, Bohr saw both its brilliance and its fatal flaw. He realized that if the atom was to remain stable, there must be something fundamentally different about the behavior of electrons, something that defied classical expectations. The early 1900s were a time of great upheaval in science. Max Planck had introduced the idea of energy quanta, that energy is not continuous, but comes in tiny packets, to explain blackbody radiation. Albert Einstein had used the same idea to describe the photoelectric effect, showing that light could behave as both a wave and a particle. These radical ideas were beginning to erode the boundaries of classical physics, but their implications for the atom were not yet clear. Bohr, with his deep insight, realized that the atom itself might be governed by these new quantum principles. He asked a simple yet revolutionary question. What if the electron does not lose energy continuously as it moves around the nucleus? What if it can exist only in certain specific orbits, and only when it jumps from one orbit to another does it emit or absorb energy? This idea, as bold as it was, would change everything, but before Bohr could formulate his theory, he had to confront the full weight of the paradox that haunted atomic physics. Imagine, Bohr thought, a miniature solar system where the nucleus is like the sun and the electrons are like planets. In this picture, the electrons circle the nucleus at high speed, held in place by the attraction of opposite charges. Now, if this analogy were true, each orbiting electron should behave like an accelerating charge, and therefore should radiate electromagnetic waves. These waves carry energy away, which would mean the electron is constantly losing energy. As it loses energy, it should move closer to the nucleus, speeding up as it falls and radiating even more energy in a fatal spiral until it crashes into the core. The collapse should be nearly instantaneous. Yet, in the real world, atoms endure for billions of years. Something was protecting them, some unseen rule that kept the electrons from falling inward. Bohr wanted to find that rule. The problem was not just technical but philosophical. The whole framework of physics was built on determinism, the belief that the universe followed precise, continuous laws. Bohr began to sense that this belief might not hold at the smallest scales of reality. There was something discontinuous, something granular about nature itself. Planck had introduced his constant, h, to express this discreteness in radiation, but no one had yet dared to apply it to the atom's internal structure. Bohr did. He decided that if energy comes in quanta, perhaps the motion of electrons is also quantized. This idea was as radical as it was necessary. It meant that the electron could not exist in arbitrary orbits. It had to occupy specific, permitted levels of energy, like steps on a ladder. Between these steps it could not exist at all. It could leap from one to another, but never hover in between. The concept defied classical reasoning, yet it explained the unexplainable. Atoms did not fall apart because electrons were forbidden from spiraling inward. They were bound to stable orbits by the laws of quantum mechanics that were only beginning to be understood. Before Bohr, the atom was a mechanical system destined to self-destruct. After Bohr, it became a quantum system, sustained by invisible rules that transcended human intuition. But this transformation did not come easily. To the scientists of his time, Bohr's proposal seemed almost mystical. How could an electron jump from one orbit to another without passing through the space between? What did it mean to say that certain orbits were allowed and others were not? Bohr's response was calm yet profound. Nature does not owe us explanations in classical terms. It reveals itself in ways that work, even if they defy our sense of logic. The truth was that the atom's survival depended on the quantization of energy. Without it, the equations of electromagnetism would doom the atom to collapse. Bohr's insight gave a new mathematical structure to atomic theory. He proposed that the angular momentum of an electron in its orbit is an integer multiple of Planck's constant divided by 2p. In simple terms, this meant that only certain orbits were possible, those that satisfied this quantization condition. In these orbits, the electron did not radiate energy. It moved perpetually without loss, sustained by the balance of opposing forces that existed in harmony at the quantum level. When Bohr applied his theory to hydrogen, the simplest atom, the results were astonishing. The energy levels he predicted matched perfectly with the spectral lines observed in hydrogen's emission spectrum. For the first time, the mysterious colors of light emitted by atoms could be explained by precise mathematical laws. Each color corresponded to a specific quantum jump. An electron leaping between energy levels, releasing a photon whose energy matched the difference between the two orbits. This was more than a theory. It was evidence that the quantum world was real, yet behind this mathematical triumph lay a deeper philosophical revelation. The atom's stability was not the result of mechanical balance, as in planetary motion, but of discrete energy states. Nature, Bohr realized, does not operate in smooth continua at the smallest scales. It functions in sudden leaps, in discontinuities that seem illogical but are fundamentally true. The universe, in its smallest dimension, is not a machine. It is a symphony of probabilities and quantized energies. Bohr's explanation for why atoms don't fall apart was therefore more than a scientific answer. It was a revolution in thought. It declared that reality at its core is not what we perceive through our senses or classical reasoning. It is governed by laws that operate beyond human intuition, yet give rise to the very stability that allows matter, life, and consciousness to exist. As Bohr developed these ideas, he often found himself in deep contemplation about the meaning of scientific truth. He once remarked that if quantum theory had not shocked you, you hadn't understood it. This shock was the price of discovery, a recognition that the old language of physics was insufficient to describe the strange yet beautiful order of the microscopic world. The stability of the atom, once a paradox, became a testimony to this new order. In Bohr's mind, the atom was not merely a structure of particles, it was a harmony of quantized motion. Sustained by the balance between energy and possibility, electrons, though invisible, danced in patterns dictated not by force alone, but by the mathematical poetry of quantum law. The reason atoms did not collapse was that nature had built them with quantum scaffolding, invisible yet unbreakable. Even today, when we speak of why atoms do not fall apart, we are echoing Bohr's insight. His model has long been refined and surpassed by the quantum mechanics of Schrödinger, Heisenberg, and Dirac. But its essence remains. Bohr's courage to defy classical logic and embrace the quantum unknown was the first true step into the new world of physics. It was he who explained that the universe holds itself together not through continuous motion, but through discrete, sacred steps of energy. A truth as mysterious as it is magnificent. Bohr's breakthrough did not merely solve a technical riddle, it transformed how humanity understood existence. The atom, once imagined as a miniature solar system, became a living symbol of the universe's hidden logic, a realm where certainty faded and probability ruled. In lecture halls across Europe, young scientists listened with disbelief as Bohr spoke of electrons that could remain suspended in invisible shells, immune to collapse, stable not because of mechanical support, but because of a law deeper than force. He told them that stability was not a miracle but a rule of nature itself, written in the mysterious constant that Planck had introduced years earlier. It was as though reality had a built-in rhythm, a code that dictated what could exist and what could never be. Bohr had discovered that the atom endures because nature quantizes its very heartbeat. When he presented his model in 1913, the scientific community reacted with a mixture of awe and skepticism. The equations worked astonishingly well for hydrogen, the simplest of all atoms. Each observed spectral line matched Bohr's prediction perfectly, as if the universe had been waiting for someone to write its melody in mathematical form. But many physicists still clung to the security of classical reasoning. They were uneasy with the idea that electrons could leap without traversing the space between orbits. The notion seemed to violate everything they knew about motion, energy, and continuity. Yet experiment after experiment confirmed Bohr's vision. The atom was not falling apart. Instead, it was dancing to a quantized rhythm, radiating light in discrete packets when electrons shifted levels, and remaining perfectly stable when they did not. This idea, though simple in appearance, carried profound philosophical weight. It suggested that the natural world is not infinitely divisible, that there are boundaries beyond which old laws cease to apply. It shattered the comforting illusion of a continuous, predictable universe. For centuries, scientists had sought to describe reality as a seamless fabric, where causes and effects flowed smoothly like the movement of planets or the path of rivers. Bohr's atom introduced discontinuity into the heart of nature. It implied that at its core, existence is built on jumps, on transitions, on sudden transformations that occur without warning yet follow precise rules. It was the birth of the quantum world, and Bohr stood at its threshold, looking into an abyss of wonder. In the quiet of his Copenhagen office, Bohr often pondered what these discoveries meant for human knowledge itself. If the atom was quantized, then perhaps human understanding was too, limited to specific levels, unable to see what lay between. He believed that science was not merely a collection of equations, but a dialogue between nature and the observer. The stability of atoms, in his eyes, was not only a physical fact, but a symbol of balance between chaos and order, between what can be known and what must remain hidden. This humility would later evolve into his famous principle of complementarity. But even at this early stage, its seed was already planted. Reality reveals itself in parts never whole, and its paradoxes are not contradictions, but expressions of truth. The early 20th century was a time of intellectual ferment. Einstein was revolutionizing space and time, Rutherford was uncovering nuclear secrets, and in distant laboratories experiments were confirming strange new phenomena that classical theory could not explain. Yet amid all this progress, Bohr's atomic model offered something different, a glimpse of unity. It suggested that beneath the confusion of discoveries lay a single principle, quantization. It linked the behavior of light, matter, and energy under one mathematical framework. For the first time, physicists could understand why the universe did not dissolve into chaos. Atoms did not collapse because they were governed by harmony, by laws that restricted their possibilities and preserved their structure. The same principle that made the atom stable would later explain chemical bonds, metallic conduction, and the life-giving stability of DNA itself. Bohr's insight was the seed from which all modern physics would grow. But Bohr's journey was not smooth. Many contemporaries challenged his model. They argued that his quantized orbits were ad hoc, a temporary mathematical trick without physical explanation. Bohr responded not with arrogance but with patience. He admitted that his model was incomplete, but insisted that it pointed in the right direction. Nature, he said, was whispering in the language of quanta, and humanity had only begun to learn its grammar. His humility was as revolutionary as his science. In a world of fierce egos and intellectual rivalry, Bohr remained calm, thoughtful, and open. His Copenhagen Institute became a refuge for young physicists who sought not only knowledge but wisdom, a place where arguments were intense but always guided by respect for mystery. One of those young visitors was Werner Heisenberg. Another was Erwin Schrödinger. Both would later refine Bohr's ideas and give quantum mechanics its modern mathematical form, but they always acknowledged their debt to him. Bohr had provided the vision, the courage to accept that nature could behave in ways that defied common sense. Heisenberg once said that Bohr taught him that clarity and truth are not the same. Sometimes, to be true, one must embrace uncertainty. This idea was rooted in Bohr's explanation of atomic stability. The electron did not need to obey human intuition about motion. It existed in a realm of probability, and its position or momentum could only be described statistically. The atom's survival, therefore, was a balance of uncertainty itself, a delicate harmony between the known and the unknowable. The realization that uncertainty was not a flaw but a fundamental feature of reality marked the true revolution. Before Bohr, ignorance was something to be eliminated. After Bohr, it became a principle of existence. The atom did not collapse precisely because it was not a mechanical object following deterministic paths. It was a system governed by wave-like rules, where stability emerged from quantized restrictions and statistical behaviors. This insight would later inspire the wave equation of Schrödinger, which replaced Bohr's orbits with probability clouds, and Heisenberg's matrix mechanics, which described transitions directly without visual images. Yet the heart of it all remained Bohr's question: why do atoms persist? And the answer, still resonating through the corridors of science, is that they obey the hidden symmetry of the quantum. Bohr's explanation changed not just physics but philosophy. It challenged the notion of absolute truth. If atoms obeyed different rules from the macroscopic world, then knowledge itself was conditional, context-dependent. What was true in one scale might not be true in another. This realization opened doors to new ways of thinking about existence, consciousness, and even morality. For Bohr, science was a way to explore these frontiers, not to conquer them. He often said that every great discovery begins with the recognition of paradox. The paradox of the atom, that it should collapse but doesn't, became a metaphor for life itself. We exist on the edge of instability, yet we endure because of invisible balances that hold us together. As the 1920s unfolded, the quantum revolution gained unstoppable momentum. Bohr's model was refined, tested, and extended. The old deterministic universe gave way to one of probabilities and potentialities. The new theory explained not only atomic spectra, but also chemical behavior, light emission, and the properties of solids. The stability of matter was no longer a mystery. It was the natural consequence of quantized energy levels. When we look around at the solidity of the world, we are witnessing Bohr's insight in action. Electrons confined to stable states, dancing endlessly around nuclei, yet never colliding, never collapsing. Sustained by the mathematics of quantum law, every object, from a mountain to a raindrop, owes its existence to this invisible balance. The everyday world is built on Bohr's stability. In his later years, Bohr reflected on how this discovery had altered human understanding. He recognized that the quantum world was not separate from us, but part of us. The same principles that kept atoms intact governed the thoughts in our brains and the stars in the sky. He believed that complementarity, the idea that contradictory descriptions can both be true, was not only a scientific principle, but a universal one. The atom, in its balance of opposites, mirrored life's own dualities: order and chaos, certainty and doubt, matter and energy. To Bohr, explaining why atoms don't fall apart was equivalent to explaining why existence holds together despite its contradictions. He often told his students that nature is not absurd, it is our expectations that are too narrow. The universe is not built to satisfy human logic. It reveals its logic slowly, in ways that demand humility and imagination. Bohr's discovery was not simply about atoms, it was about the limits of human perception. The collapse that never happens is a reminder that stability emerges from laws beyond sight, from quantized patterns that govern all matter. Every time we light a candle or watch a star, we are witnessing the triumph of Bohr's principle, the persistence of structure in a universe that might otherwise dissolve into chaos. When Bohr received the Nobel Prize in 1922, he dedicated his achievement not to himself, but to the collective spirit of discovery that guided science. He saw his model as one step on a long journey toward understanding. Yet the world recognized that his contribution had changed the course of history. He had explained the impossible, why matter exists. In doing so, he gave humanity the key to unlocking energy, chemistry, and the technologies that would define the modern age. From semiconductors to lasers, from nuclear power to medical imaging, every quantum-based invention traces its ancestry back to Bohr's question about the atom's stability. And yet, despite the practical wonders that followed, Bohr never lost sight of the mystery. He remained deeply philosophical, often saying that the task of science is not to eliminate mystery but to deepen it. The more we understand, the more profound our sense of wonder becomes. The atom's refusal to collapse is not just a physical fact. It is a poetic symbol of resilience, a whisper from the universe that order can arise from uncertainty. Bohr's life itself reflected this balance. He navigated war, political turmoil, and ethical dilemmas during the atomic age, always advocating for wisdom over power. Even as his ideas paved the way for nuclear energy, he called for the peaceful use of science, insisting that understanding should serve harmony, not destruction. In the quiet moments of his later life, Bohr would gaze at the night sky and imagine the countless atoms within each star, vibrating, radiating, existing by the same rule he had uncovered decades earlier. He must have felt both humbled and uplifted by the realization that the same principle sustaining the cosmos sustained him. The human body, every breath, every heartbeat. Each was a dance of stable atoms, each a testament to the quantized order he had described. To understand why atoms don't fall apart was to glimpse the architecture of creation itself. Today, more than a century after Bohr's first papers, his insight continues to echo through physics. Modern quantum field theory, the Standard Model, and even the search for quantum gravity all rest on the foundation he built. The electron's stability, once a paradox, is now a cornerstone of reality. Yet, in a sense, the question remains open. We know the mathematics, but the mystery of why nature chose quantization remains profound. Perhaps it is simply the universe's way of maintaining coherence, an eternal balance between freedom and constraint, between the infinite and the discrete. Bohr's genius lay in seeing that stability and freedom are not opposites but partners in the cosmic dance. If we could travel inside an atom, we would see nothing solid, just waves of probability, vibrations of energy confined to invisible orbits. And yet, from this emptiness arises everything: color, form, life. The electrons do not fall because they are not truly particles circling like moons. They are standing waves, existing only where their quantum conditions allow. Bohr intuited this before it could be proven, guided by a mixture of logic and imagination that only a few possess. He trusted that nature's strangeness was not chaos, but a higher kind of order. The atom, stable and eternal, was the universe's signature of design. In the end, Bohr's explanation of why atoms don't fall apart is not only a chapter in physics, it is a revelation about being itself. It tells us that stability is born from constraint, that beauty emerges from limitation, that the universe endures because it has learned to balance opposites. The same principle that holds electrons in orbit holds planets in space, hearts in rhythm, and civilizations in harmony. We exist because nature has found a way to keep its smallest parts from collapsing. The miracle of stability is the foundation of all creation. As the camera of imagination pulls back from the atomic scale to the vastness of the cosmos, we see that Bohr's discovery connects everything: the micro and the macro, the particle and the star, the human and the divine. The atom's persistence is the universe's promise that even in the face of tension and uncertainty, equilibrium can prevail. Matter endures not by resisting change, but by quantizing it, transforming energy into structure, chaos into pattern. That is Bohr's enduring message. The universe does not fall apart because it is built on steps of light, on quanta that bind existence together. And so the question that once haunted physics, why don't atoms collapse, has become a metaphor for something larger. It reminds us that in every system, from the smallest particle to the human spirit, there exists a hidden order, an invisible law that sustains being. Niels Bohr revealed that law to the world, not as dogma but as a vision. Through his work, we learned that the stability of the atom is the stability of the cosmos itself, a fragile yet eternal dance of energy held by quantum grace. When the young Niels Bohr entered the scientific world, it was a time of both brilliance and confusion. Physics had reached unprecedented heights. Maxwell's equations had unified electricity, magnetism, and light. Einstein had redefined space and time, and Rutherford had uncovered the hidden architecture of the atom. Yet beneath all this triumph lay a silent crisis. Classical physics could no longer explain the simplest question in the universe: why matter exists in a stable form. It could predict the orbits of planets, the trajectory of projectiles, and the propagation of waves, but when it looked inward, toward the invisible architecture of atoms, its laws began to crumble. The equations that had once seemed eternal now predicted a self-destructing universe, a cosmos that should have vanished the moment it began. Bohr saw in this crisis not failure but opportunity. Where others saw contradiction, he sensed a door opening into a deeper layer of truth. His mind was unlike others, poetic yet precise, philosophical yet mathematical. To him, the atom was not merely a mechanical system. It was a metaphor for the universe's inner order. He believed that the rules governing the smallest scales must differ from those that rule the visible world, and he was willing to abandon centuries of tradition to find them. This willingness to let go of the familiar marked the beginning of his revolutionary vision. When Bohr joined Rutherford's laboratory in Manchester in 1912, he was stepping into the heart of atomic mystery. Rutherford's nuclear model had revealed that most of the atom was empty space, with almost all its mass concentrated in a tiny nucleus. But the model left an unbearable contradiction. The electrons orbiting that nucleus should lose energy as electromagnetic radiation and spiral into the core. The very laws that had made classical physics great were now its undoing. Bohr knew that to explain the atom's stability, one would have to rewrite those laws, not slightly adjust them but reimagine them completely. His inspiration came from an idea that had been circulating in the shadows of scientific thought: Max Planck's quantum hypothesis. Planck had proposed that energy is not continuous but comes in discrete packets, quanta, each proportional to the frequency of radiation. It was a desperate mathematical trick to fit experimental data, but it worked. Einstein, a few years later, extended this idea to light itself, showing that light could behave as a stream of particles, photons, capable of ejecting electrons from metal surfaces. These ideas were revolutionary, but even Einstein hesitated to apply them beyond radiation. Bohr, however, saw their deeper significance. If energy could be quantized in light, why not in matter? Perhaps the atom itself was built on the same principle, a structure of quantized motion rather than continuous flow. This thought became the seed of his revolution. Bohr began to imagine that electrons could occupy only specific energy levels around the nucleus, stable orbits where they did not radiate energy. They could not exist in between these levels. They could jump from one orbit to another, absorbing or emitting a quantum of energy equal to the difference between levels, but in their orbits they remained perfectly stable. It was a radical departure from all known physics, yet it held the key to the atom's survival. To the classical mind, this was madness. It defied every rule of motion. An orbit without energy loss was unthinkable. A jump without a path was absurd. But Bohr cared little for convention. He trusted nature more than theory, and nature, as experiment showed, was whispering something new. He tested his idea on the simplest atom, hydrogen, and the results were astonishing. His equations reproduced the exact spectral lines observed when hydrogen emitted light. Each line corresponded to an electron's jump between quantized levels, each photon carrying the energy difference. The model worked not because it was logical, but because it was true. This success was more than a calculation, it was a revelation. Bohr had uncovered a law that united energy and structure, light and matter. He had turned the chaotic behavior of atomic spectra into a symphony of numbers. The stability of matter was no longer a mystery, it was a direct consequence of quantization. The atom did not fall apart because its electrons were bound to discrete energy states, unable to radiate continuously. Bohr's revolutionary vision had transformed a collapsing universe into a coherent one when he published his findings in 1913 under the title On the Constitution of Atoms and Molecules. The scientific world trembled. The paper was dense, filled with equations. But beneath the mathematics lay an idea so audacious that even Einstein paused in admiration. Sommerfeld, Born and Pauli, future titans of quantum mechanics, read Bohr's words and saw a new dawn approaching. The atom was no longer a mechanical system but a quantized organism, alive with rhythm and rule. Yet Bohr's genius was not just in his equations, it was in his imagination. He saw the atom as a bridge between the visible and the invisible, the classical and the quantum. He realized that nature speaks two languages, one for the large and one for the small, and that human beings must learn to translate between them. His model was an act of translation, turning the chaos of quantum behavior into something the human mind could grasp, if only partially. To understand the depth of Bohr's vision, one must remember how radical it was in its time. Physics then was still intoxicated by determinism. Every event, it was believed, had a precise cause, and the future could be predicted if the present were known. Bohr shattered that dream. His atom was not deterministic, it was probabilistic. An electron could jump unpredictably from one orbit to another, emitting light in sudden flashes. These jumps were not caused by external forces, but by the internal structure of the atom itself. Spontaneous, discrete, and governed by the quantum law, the universe, Bohr declared, is not a machine, but a dance. This dance was orderly but not mechanical. It followed mathematical harmonies that transcended human intuition. The electron's stability was not due to inertia or balance, but to the quantization of angular momentum, a mysterious rule that stated an electron's motion could only occur in multiples of Planck's constant divided by 2p. That constant, h, became the signature of Bohr's vision, the key that unlocked the secret of the atom. In every stable orbit, the electron's angular momentum was nh2p, where n was an integer. These simple numbers defined the architecture of matter itself. When Bohr shared these results with Rutherford, his mentor was astonished. The older man, a master of experiment but wary of speculation, could not believe that such a simple quantization rule could hold the atom together. "How does the electron know where to stop?" Rutherford asked half-jokingly. Bohr smiled. "It doesn't stop," he replied. "It simply cannot exist elsewhere." It was an answer that captured the essence of his revolution, the idea that nature is not a matter of choice or chance, but of necessity written in quantum form. As word of Bohr's theory spread, it ignited both enthusiasm and controversy. Some called it genius, others called it nonsense. But its predictions spoke louder than opinions. Spectroscopy, the study of light emitted by atoms, became the testing ground. Every atom had its unique spectral fingerprint, a series of bright and dark lines corresponding to energy transitions. For decades, these lines had defied explanation. Bohr's model decoded them perfectly for hydrogen, and though it struggled with more complex atoms, it pointed the way forward. The atom, once a mysterious enigma, had become a quantized instrument, playing the music of the universe. The philosophical implications were even greater. Bohr's model forced scientists to accept that the microscopic world followed rules fundamentally different from those of everyday experience. Continuity gave way to discontinuity, predictability to probability, certainty to mystery. The revolution was not just scientific but spiritual. It challenged humanity's conception of knowledge itself. No longer could we assume that the universe was transparent to reason. Bohr showed that nature allows us glimpses of truth only through the language it chooses, a language that is sometimes discrete, sometimes paradoxical, but always consistent within itself. The beauty of Bohr's vision lay in its humility. He never claimed to have discovered the ultimate truth. He knew his model was provisional, an approximation of something deeper. He once wrote that truth in science is never final. It is like a sculpture that becomes clearer as each generation carves away at ignorance. His revolutionary step was to admit that our classical tools, equations, measurements, and logic, might not fully capture reality at its core. The quantum world, he realized, could not be pictured. It could only be described through mathematics and experiment. As he refined his theory, Bohr found patterns that hinted at an underlying unity. The same quantization that stabilized atoms also appeared in the vibrations of molecules and the emission of light. Nature, it seemed, operated through discrete units of action, tiny, indivisible quanta that governed every process from radiation to rotation. The classical notion of continuous energy flow was gone forever. In its place stood a new architecture of reality, where stability emerged from restriction and freedom coexisted with confinement. Bohr's revolutionary vision thus redefined what it meant to explain something scientifically. He did not eliminate mystery, he formalized it. His model did not describe how electrons moved, it described where they could exist. It did not trace their paths, but mapped their possibilities. This shift from trajectory to state, from cause to condition, was the essence of quantum thought. It allowed physics to move beyond visualization and embrace abstraction. The atom, once imagined as a tiny solar system, now became a realm of potential energy levels and quantum leaps. The mechanical universe had evolved into a symbolic one. Bohr's contemporaries struggled to adapt. To them, his model felt incomplete, even mystical, but time vindicated him. Every experimental result that followed confirmed his quantization rule. The ultraviolet catastrophe that had haunted classical physics vanished, spectral lines lined up perfectly, and chemical behavior found its explanation in the arrangement of quantized electrons. The revolution was complete. Bohr had not just explained why atoms don't fall apart, he had shown that they endure because of quantization, because nature operates in discrete steps rather than continuous slides. The consequences extended far beyond atomic physics. Bohr's ideas paved the way for the entire field of quantum mechanics, which would soon transform everything from chemistry to electronics, from lasers to computers. Yet, at the heart of all these innovations remains his original insight: stability arises from quantized order. Without Bohr's vision, the solid world would be an illusion. Matter would be impossible. His theory became the invisible scaffolding of reality, holding every object, every molecule, every breath of air in its quantized embrace. But Bohr was never satisfied with mere success. He continued to question his own work, seeking deeper meaning. He wondered what it truly meant for energy to be quantized, for motion to occur in jumps. Was it a feature of nature itself, or a limitation of human observation? These questions haunted him, driving him to explore not just the physics, but the philosophy of the quantum world. He sensed that at its heart lay a profound lesson about existence, that reality, in its smallest parts, is defined not by what is, but by what can be. The universe, he concluded, is a tapestry of possibilities woven together by observation. As Bohr's ideas matured, so too did his influence. Young physicists flocked to Copenhagen, drawn by his clarity of thought and his openness to paradox. His institute became a sanctuary for curiosity, a laboratory of ideas where the boundaries between science and philosophy blurred. Under his guidance, quantum theory evolved into a coherent framework, giving birth to the modern understanding of matter. But even as his students formalized the mathematics, Bohr remained the philosopher of the quantum, the one who saw not just equations but meaning. His revolutionary vision was thus not a single discovery but a way of seeing, a lens through which to interpret the universe. It taught that progress comes not from clinging to certainty, but from embracing contradiction, that truth reveals itself through limitation, and that stability, whether in atoms or in life, depends on the unseen quantization of possibility. Bohr's vision matured in the years that followed, not as a fixed theory, but as a living philosophy of nature. He understood that his model of the atom was an imperfect window into a deeper truth. Yet he also knew that every window, no matter how small, reveals a portion of the infinite. When he looked at the hydrogen spectrum and saw order emerging from apparent chaos, he realized that nature's elegance often hides behind boundaries that human intuition cannot cross. Those narrow paths of stability where electrons moved were not random. They were the signposts of a quantized universe, a whisper that reality itself is made of limits. To most of his contemporaries, these limits seemed artificial. They asked, "Why can't electrons move freely through space, radiating energy continuously?" Bohr answered softly but firmly, "Because freedom without structure is destruction. In the microscopic world, stability is born from restriction. The atom does not collapse because it obeys a rule that denies infinite possibilities. It is as if nature, to preserve itself, built fences around chaos. Those fences were the quantized orbits that Bohr had defined, each one a sanctuary where the electron could dwell without decay. He had discovered that permanence is not the absence of change, but the balance of it. This way of thinking, both scientific and philosophical, gave Bohr's work an almost spiritual depth. He began to see quantization not merely as a mathematical artifact, but as a universal principle. Every stable phenomenon, from atomic spectra to the orbits of planets, followed patterns of balance between opposites, attraction and repulsion, motion and stillness, order and uncertainty. Bohr's atom was a reflection of that cosmic equilibrium. The electron could move, but only in ways that maintained harmony with the whole. It could emit energy, but only in precise amounts that preserved the unity of the system. In this sense, Bohr's vision went beyond physics. It was a philosophy of existence encoded in numbers. When the first generation of quantum pioneers gathered around him in Copenhagen, Bohr became both teacher and interpreter. His discussions were legendary, long, intense, and filled with silence as much as speech. He would pause for minutes before answering a question, as if weighing the metaphysical weight of every word. To him, scientific statements were never isolated facts. They were fragments of a dialogue between humanity and the universe. His revolutionary vision was not to impose meaning on nature, but to listen to it carefully, to let the atom speak through experiment and mathematics. The atom, he believed, was not a mechanical toy to be dissected, but a mystery to be understood through patience and humility. As his ideas spread, they began to reshape not only physics, but the collective imagination of an era. Artists, philosophers, and poets were drawn to the implications of quantization. The old dream of an ordered, deterministic universe faded, replaced by a vision of fluid possibilities. Bohr's theory had given birth to uncertainty, but it was a creative uncertainty, a fertile ground where new understanding could grow. The world was no longer a clockwork, it was a living organism, unpredictable yet harmonious. The rules that held the atom together also held galaxies, ecosystems, and human hearts. Everything persisted because it existed within boundaries that allowed freedom without collapse. Bohr's own life mirrored this delicate balance. He was calm yet intense, private yet profoundly social. His home became a haven for discussion, where physicists debated equations at the dinner table and children listened to the murmurs of ideas that would define the century. During walks through Copenhagen's quiet streets, he would speak softly about complementarity, the belief that truth has multiple faces and that understanding comes from holding opposites together. This idea grew naturally from his atomic theory. Just as light could be both wave and particle, so too could knowledge be both objective and subjective, depending on how one approached it. Reality, Bohr realized, is not a single picture but a collage of perspectives. This revolutionary way of thinking allowed him to resolve conflicts that others found paralyzing. When Einstein challenged the probabilistic nature of quantum mechanics, insisting that God does not play dice, Bohr replied with gentle certainty, "Stop telling God what to do." He did not mean it as arrogance, but as humility, the recognition that nature's methods are beyond human authority. For Bohr, the atom was not disorderly because it was probabilistic. It was stable precisely because it was. The unpredictability of quantum jumps was not chaos. It was the very mechanism that preserved balance. Atoms did not fall apart because uncertainty itself was a law, ensuring that electrons could never lose all energy and collapse into the nucleus. The universe, it turned out, maintained order through the grace of unpredictability. Bohr's revolutionary vision therefore redefined the meaning of knowledge. To know something was no longer to pin it down with certainty, but to understand the conditions under which it could be known. In the laboratory, every observation disturbed what it measured. The observer became part of the phenomenon. Bohr embraced this as natural, not as a flaw. He saw in it a reflection of human existence itself. Our presence shapes reality. Our choices define outcomes. Our questions determine the answers we find. The atom, in its quiet stability, was a mirror of the human condition, fragile, uncertain yet enduring through balance. By the mid-1920s, Bohr's early atomic model was being overtaken by new mathematics. Schrödinger's wave equation described electrons not as particles in orbits, but as standing waves spread across space. Heisenberg's matrix mechanics replaced visual imagery with pure abstraction. At first glance, these theories seemed to contradict Bohr's picture, but Bohr recognized them as deeper expressions of the same truth. The quantized orbits of his model became quantized states in the new language of quantum mechanics. The principle of energy levels remained untouched. Even as his own model was surpassed, its essence lived on, embedded in every equation that followed. Bohr's revolution was not a theory to be discarded. It was the foundation upon which all later theories stood. As experiments confirmed the predictions of quantum mechanics with uncanny precision, Bohr's vision gained the authority of reality itself. The once invisible rules he had intuited were now measurable, repeatable, undeniable. Yet he continued to remind his students that understanding does not mean possessing. Every word we utter, he said, must be used with care, as if it were explosive. To describe the atom was to touch the edge of mystery. Each success brought deeper questions. What determines an electron's jump? Why is Planck's constant what it is? Could there be a reality beneath probability, or was probability itself the fabric of existence? Bohr answered with silence, because he knew that silence sometimes contains more truth than speech. The impact of his revolution soon reached far beyond the laboratory. The technologies of the 20th century, semiconductors, transistors, lasers, nuclear energy, all trace their origin to Bohr's insight that atoms are quantized. Every electronic device, every glowing screen, every spark of modern civilization hums with the rhythm of his discovery. Yet Bohr himself remained detached from material triumph. To him, the true significance of his vision was not technological power, but philosophical transformation. Humanity had learned that nature's logic is subtler than ours, that beauty arises from restriction, and that existence itself is an act of balance. The atom was proof that perfection lies not in rigidity, but in harmony between extremes. In the 1930s and 1940s, as the world descended into war and the quantum discoveries were weaponized, Bohr faced a new kind of dilemma. His theory had helped unlock the energy of the atom, but that same knowledge threatened to destroy what it had illuminated. He responded not as a politician but as a philosopher-scientist. He advocated for openness, for the sharing of scientific knowledge among nations, believing that secrecy breeds fear and that fear leads to collapse, just as an atom deprived of equilibrium collapses. To him, peace itself was a form of quantization, a state maintained by balanced forces, fragile yet enduring when harmony is respected. Even in the chaos of geopolitics, Bohr's revolutionary vision guided him toward balance. After the war, he returned to Copenhagen to rebuild his institute and his ideas. Younger generations saw him as both legend and sage. They came to debate not only physics but meaning. Bohr listened more than he spoke, allowing them to discover truths for themselves. He had become the custodian of a worldview that united science and philosophy. When visitors asked him how he felt about his early model being replaced by more advanced theories, he would smile. "Theories are like staircases," he said. "You use the steps to climb higher, but you never pull them away." The Bohr model had lifted humanity out of the darkness of classical contradiction and into the light of quantum understanding. It had explained not only the stability of matter, but the pattern of progress itself, one quantized step at a time. As he aged, Bohr continued to refine his thoughts on complementarity, seeing it as the ultimate expression of his atomic insight. Just as an electron can be both wave and particle, human understanding can be both rational and poetic. Science and philosophy, measurement and intuition, each reveal different aspects of the same truth. The world does not collapse under the weight of contradiction. It thrives because of it. This was the essence of his revolutionary vision, that opposites coexist, not in conflict but in completion. Atoms endure because they reconcile attraction and motion, energy and restraint. Humanity, he believed, must do the same. In the quiet of his final years, Bohr would sometimes reflect on the strange path that had led from curiosity to cosmos. He had started with a paradox, why doesn't the atom fall apart, and found an answer that reshaped the foundations of knowledge. Yet he always felt that the true discovery was not the answer but the humility it inspired. To explain why atoms endure was to glimpse the wisdom of nature, to understand that existence itself is an act of continual balance. Every particle, every quantum leap, every flicker of light is a negotiation between chaos and order. In that negotiation lies the secret of being. Even today, Bohr's revolutionary vision continues to echo through science. Quantum mechanics has evolved into quantum field theory, and new mysteries, dark matter, quantum entanglement, the fabric of space-time, have taken center stage. Yet the spirit of Bohr's insight remains unchanged. Every stable system, from the orbit of an electron to the coherence of a laser beam, is a manifestation of quantized harmony. The laws he helped uncover still govern the devices we hold, the stars we observe, and the DNA that encodes life. His discovery was not merely about atoms, it was about the architecture of permanence. To watch an atom through the lens of Bohr's theory is to witness a miracle of restraint. Inside that tiny space, energy seethes with unimaginable intensity, yet it remains contained, structured, balanced. Electrons flicker between states, photons are born and vanish, and through it all, the nucleus holds firm, bound by forces that obey quantized laws. Without those laws, the universe would collapse into radiation. With them, it becomes form and matter, music and mind. Bohr's vision turned instability into existence, randomness into rhythm. The atom became the first cathedral of the quantum age, and Bohr its quiet architect. It is impossible to overstate the transformation he brought about. Before Bohr, physics sought certainty. After Bohr, it sought understanding. The change seems subtle but is profound. Certainty demands closure. Understanding accepts openness. Certainty collapses under contradiction. Understanding absorbs it. Bohr taught the world to see contradiction as a source of strength. Just as electrons cannot exist without quantized limitation, human thought cannot advance without paradox. In this way, his revolution extended beyond laboratories. It touched the essence of wisdom itself. He once remarked that the opposite of a profound truth may also be true. In those few words he captured the spirit of his lifetime of inquiry. The atom's stability and its dynamism are opposites, yet both are true. The universe is both predictable and unpredictable, bound and free, simple and incomprehensible. To Bohr, this was not confusion, but completeness. The revolutionary power of his vision lay in its acceptance of duality, its recognition that reality is richer than any single description. Science, philosophy, and even art continued to draw from that insight. When Niels Bohr died in 1962, the world mourned not only a physicist but a philosopher of existence. His equations live on, but so does his way of seeing. Every time a student learns that electrons occupy discrete energy levels, they inherit his understanding that the universe is built on quantized harmony. Every time an engineer designs a transistor or a quantum computer, they apply the same principles that once existed only in Bohr's imagination. The atom still stands, silent and stable, a monument to his thought. And perhaps somewhere, in the quiet hum of matter, the universe still whispers the lesson he uncovered, that stability is not a gift of stillness, but of motion in perfect rhythm, that freedom is meaningful only within the boundaries that sustain it, and that every existence, from the smallest particle to the grandest star, survives because it obeys a law of balance written in the quantum script of creation. Bohr's revolutionary vision remains that eternal law translated into human words. In the strange and beautiful architecture of the atom, Niels Bohr discovered something that seemed to defy reason, the idea that electrons do not glide smoothly between energy levels, but instead leap, instantaneously, discontinuously, without warning. These leaps, which he called quantum jumps, were the heartbeat of matter itself, the pulse of stability that allowed the universe to exist. To classical physics, such behavior was absurd. The notion that an electron could disappear from one orbit and reappear in another without traversing the space in between sounded like magic. But in the quantum world, this magic was law, and Bohr had uncovered it. The concept of quantum jumps was not born from speculation, but from necessity. When Bohr examined the hydrogen spectrum, he saw patterns of light that could not be explained by continuous motion. The atom emitted light only at specific frequencies, as if it were playing a melody of precise notes rather than a chaotic hiss. Each frequency corresponded to a specific difference in energy, a gap between two distinct levels within the atom. The only possible explanation was that the electron was not moving through a gradual transition, but was jumping abruptly from one allowed orbit to another, releasing or absorbing a quantum of energy in the process. That quantum was not arbitrary. It matched exactly the difference between the energy levels. The jump was instantaneous, yet it produced light that traveled across the universe. This idea transformed the meaning of motion itself. In the world of Newton and Maxwell, movement was continuous, predictable, and smooth. In Bohr's world, motion could occur in sudden bursts, discrete changes that shattered continuity. The electron did not spiral inward like a planet losing momentum. It existed in defined states, and only through a quantum jump could it change from one to another. In between, there was no halfway, no gray zone. Either it was here or there. The classical universe of seamless cause and effect was gone. In its place stood a new reality where stability came from discontinuity, a paradox that would redefine science and philosophy alike. For Bohr, these jumps were not flaws in nature, but the very reason atoms did not fall apart. They prevented the constant drain of energy that classical physics predicted. In his model, electrons could occupy only those orbits where their angular momentum was an integer multiple of Planck's constant divided by 2 pi. These orbits were stable, they did not radiate energy. The electron could stay there indefinitely, forever circling the nucleus without decay. Only when it was disturbed, when energy was added or taken away, could it jump to a different orbit. The stability of matter was thus born from this quantized structure, from the forbidden zones between levels that electrons could never enter. Nature had built invisible walls into the heart of the atom, and those walls kept existence intact. The philosophical implications of this discovery were immense. It meant that nature operates not in smooth gradients, but in steps. That change happens not as a slow evolution, but as a leap, abrupt, irreversible, and exact. Between one quantum state and another, there was no path, no in-between. The old vision of reality as a continuous film of events was replaced by a universe of frames, flickering one after another at unimaginable speed. Every photon of light, every chemical reaction, every heartbeat of existence was governed by these quantum jumps. Bohr's insight turned the atom into a stage where the drama of creation unfolded in discrete acts. At first, even Bohr struggled with the strangeness of his own idea. How could an electron vanish from one orbit and appear in another without crossing the space between? What happened during the transition? Where was the electron in the instant of the jump? The questions were unanswerable, not because Bohr lacked imagination, but because nature refused to offer a picture that fit human logic. He realized that the quantum world could not be visualized in the same way as the macroscopic one. Its processes were not mechanical but mathematical, not continuous but conditional. The electron's journey from one state to another was not a path through space, but a transformation of possibility. It did not move through distance. It changed its identity. To explain this, Bohr used an analogy that still echoes through physics. When an electron jumps from a higher orbit to a lower one, it emits a photon, a particle of light, carrying the exact energy difference between the two states. The light we see, from the glow of stars to the flicker of a candle, is the direct result of these quantum jumps. Every color corresponds to a specific energy difference, a unique transition between levels. The universe itself, shining with countless hues, is a symphony of quantum leaps. What we call light is the visible memory of these transitions, the signature of matter rearranging itself in discrete steps. This revelation was breathtaking, not just scientifically but philosophically. It meant that stability is born from motion, and motion is defined by leaps. Atoms remain intact because their electrons are trapped in quantized orbits, forbidden from decaying gradually. They can only change by jumping, and each jump obeys strict rules of energy conservation. There is no chaos in this apparent randomness, only order hidden in discontinuity. Nature, Bohr realized, is precise even when it seems unpredictable. It measures every change, every photon, every vibration with mathematical perfection. As Bohr developed his theory, he began to see that these quantum jumps were not isolated phenomena but universal patterns. They appeared in the emission of light, in the absorption of energy, in chemical reactions, and even in the behavior of solids. Wherever change occurred, it happened in steps, not flows. The world, at its core, was digital long before humanity invented the word. The analog illusion of continuity was a product of scale. Beneath it, everything operated in quantized transitions. This realization changed not only physics, but the way humanity understood time, energy, and life itself. Every heartbeat, every thought, every flash of lightning was, in a sense, a cascade of quantum jumps. Bohr's discovery also redefined the relationship between cause and effect. In the classical world, every event had a traceable origin, a chain of forces stretching infinitely backward. In the quantum world, this chain was broken. The jump itself was unpredictable. It could happen at any moment. One could calculate the probability of a transition, but never its exact timing. This was not a limitation of technology or measurement. It was a fundamental feature of reality. Nature itself played by rules of probability, not certainty. The electron did not decide when to jump. It existed in a state of readiness, a cloud of potential, until energy tipped the balance. This was the seed of what would later become the quantum interpretation of nature, a universe of possibilities collapsing into reality through discrete acts. The stability of matter thus depended on two opposing principles: quantization and uncertainty. Quantization defined where electrons could exist. Uncertainty defined when they could change. Together they created a delicate equilibrium that made the universe both stable and dynamic. Without quantization, atoms would collapse. Without uncertainty, they could never evolve. Bohr's model balanced both forces perfectly, describing a reality that was both ordered and alive. It showed that stability is not stillness but rhythm, a perpetual interplay between the allowed and the forbidden, the known and the unknown. When Bohr shared his ideas with the scientific community, the reactions ranged from wonder to disbelief. Some physicists, still loyal to classical mechanics, rejected the notion of jumps as unscientific. They demanded to know what happened between the orbits, what physical mechanism caused the leap. Bohr replied with calm conviction, "Nothing happens between, because there is no between. The electron does not travel, it transforms." His answer was not an evasion, but a revelation. It signaled a new era in science, where the goal was no longer to visualize processes but to describe them mathematically. Nature's truth, Bohr realized, could not always be seen. It could only be understood. His courage to accept this invisible logic was what set him apart. Many of his peers, including Einstein, struggled with the idea that randomness and discontinuity could form the foundation of reality. Einstein famously said that God does not play dice, but Bohr saw the game differently. It was not that nature played dice, it was that we mistook the rules. The universe was not gambling, it was quantized. The unpredictability of quantum jumps did not mean chaos but a deeper kind of order, one governed by laws beyond the reach of deterministic thinking. Each jump obeyed the conservation of energy perfectly. Each photon matched the difference between states exactly. The unpredictability lay not in the rule but in the timing. Even randomness, Bohr realized, has structure. In this sense, quantum jumps were the bridge between freedom and law. They showed that the universe could be both spontaneous and precise, both uncertain and stable. The atom's resilience came from this paradox. Electrons free to jump yet bound by quantized energy. That combination created the permanence of matter and the possibility of change. Without these leaps, there would be no light, no chemistry, no life. Every molecule formed, every bond broken, every star that shines owes its existence to the dance of quantum jumps. The universe is illuminated by their rhythm. Bohr's insight also had profound implications for human understanding. It suggested that change in the universe is not continuous progress but a series of leaps. Knowledge, too, evolves in jumps, sudden insights that transform our worldview. Between those leaps lies stillness, preparation, potential. In that sense, Bohr's atom was a metaphor for discovery itself. Science advances not by smooth accumulation but by quantum transitions, revolutions of thought that rearrange the entire structure of understanding. The stability of truth, like that of atoms, depends on the coexistence of old states and new, bound by the energy of transformation. The discovery of quantum jumps thus became more than a scientific breakthrough, it became a philosophy of existence. It told humanity that stability and change are not enemies but partners, that continuity is an illusion woven from countless discrete acts of creation. Every breath of wind, every flicker of consciousness, every photon that touches the eye is part of this dance. The universe does not flow. It flickers. It exists through jumps, sustained by a rhythm that no clock can measure but every atom obeys. Bohr's revolutionary idea would later find confirmation in countless experiments. Scientists observed electrons emitting photons exactly as his theory predicted. They measured the frequencies, matched the energies, and saw the universe behave with uncanny precision. Each observation strengthened Bohr's conviction that reality, though strange, was consistent. Nature might be mysterious, but it was not irrational. The atom's stability was not a miracle, it was a rule written in quanta. As the years passed, the phrase quantum jump entered everyday language, often used to describe sudden progress or transformation. Few realized how literal the metaphor was. Every light bulb, every chemical reaction, every heartbeat depends on real quantum jumps. Electrons moving between energy levels, releasing light, and binding atoms together. The stability of the world is built upon their invisible leaps. We live quite literally in the afterglow of Bohr's discovery. The deeper Bohr explored the nature of these quantum jumps, the more he understood that they were not mechanical accidents but the language of existence itself. He began to realize that what appeared as abruptness was, in truth, the most precise coordination imaginable. Each electron, though invisible, obeyed a code so strict that every jump was measured down to the smallest fraction of Planck's constant. There were no errors, no wasted motion, no deviation. The atom functioned like a symphony where every note was struck at exactly the right instant, yet no conductor was visible. The harmony arose from the rules themselves. That realization moved Bohr beyond physics. It became almost a meditation on order within uncertainty. He saw that each quantum jump preserved energy with absolute fidelity. When an electron descended to a lower orbit, it released a photon whose energy exactly equaled the difference between the two levels. When it ascended, it absorbed one with the same precision. It was as if the universe balanced its books perfectly after every exchange, ensuring that no debt of energy ever went unpaid. This accounting, strict yet elegant, gave rise to all light, color and chemical behavior. Without it, nothing would shine or combine, molecules would never form, stars would never burn, and vision itself would not exist. Every flash of lightning, every glimmer on water, every spark in a child's eye is the visible trace of electrons leaping in obedience to Bohr's law. To Bohr, these transitions revealed something profound about stability. They showed that equilibrium is dynamic, not static. An atom endures not because it is motionless, but because its motions are quantized, confined to rhythms that preserve balance. In this sense, the universe maintains itself through continuous renewal, even in apparent stillness. Electrons leap, photons fly, energy circulates. The world holds together by perpetual motion, regulated by quantum discipline. That paradox, movement creating stability, became one of Bohr's lifelong fascinations. He sensed that the same principle operated everywhere, from biology to society. Vitality and order are not opposites but partners. As experiments multiplied, the evidence grew overwhelming. Each new spectral line confirmed that the energy differences were discrete, not continuous. When scientists used more powerful instruments, they saw that every element had its own pattern, a fingerprint of its internal quantum jumps. Hydrogen's pure simplicity, helium's twin lines, sodium's yellow glow, all could be traced back to electrons shifting between specific levels. The periodic table itself, once a mystery of chemistry, began to make sense through Bohr's framework. Elements differed because their electrons filled quantized shells. Chemistry was revealed as the art of quantum architecture. What bound atoms together in molecules were not arbitrary forces, but the same leaps of energy that governed light, matter, and radiation were two aspects of one quantized order. This understanding gave human beings unprecedented power. By learning how to manipulate quantum jumps, scientists could create light sources, measure time with atomic precision, and eventually harness nuclear energy. Yet Bohr viewed these achievements with caution. He reminded his students that knowledge of power brings responsibility. The same quantum transitions that illuminate could also destroy, if misused. Stability, whether in atoms or in civilizations, depended on respecting the invisible boundaries that sustain harmony. It was a moral echo of his scientific insight. Systems collapse when they exceed their quantized limits, even as others celebrated. The predictive success of his model, Bohr remained restless. He felt that the concept of quantum jumps raised deeper questions about reality. What exactly happens during a jump? Does the electron exist as a particle or as a wave? How can an instantaneous event have measurable consequences across space? These puzzles troubled him not as contradictions, but as invitations to think differently. He began to see the act of observation itself as part of the phenomenon. The jump, he reasoned, becomes real only when it interacts with something else, when a photon is emitted, when a detector registers light, when consciousness perceives a flash. Between the old state and the new lies a realm of potential, a domain where probability rules until observation crystallizes outcome. In that liminal space, reality is not fixed but fluid. This insight led Bohr toward what would later be called the Copenhagen interpretation. The atom is not a miniature machine but a field of possibilities. Its stability arises because probabilities interfere in such a way that certain states persist while others cancel out. The quantum jump, then, is the moment when potential becomes actual, when one possibility triumphs over all others. Bohr's leap was not just physical, it was metaphysical. He dared to propose that existence itself may be quantized, that the universe advances in discrete acts of realization. Every observation, every interaction, is a jump from possibility to fact. The atom's behavior thus mirrors the creative pulse of reality. To explain this to students, Bohr often used gentle paradoxes. He would say that an electron does not move from one orbit to another, the atom simply changes its state, and the electron's identity changes with it. It is not a journey but a reconfiguration of the whole system. The photon emitted is the record of that transformation. In this view, the universe conserves not only energy but coherence. Nothing is lost, only rearranged. The continuity that classical science demanded survives, but in a subtler form, the continuity of conservation within discontinuity of action. Every quantum jump affirms both difference and unity. the implications reached far beyond physics. Bohr's model suggested that reality is participatory, that events depend on context, just as an electron's state cannot be defined without specifying how it is measured. Truth cannot exist without perspective. This idea, radical in science, resonated with philosophy, psychology, even art. Painters began to experiment with fragmentation and reconstruction, composers with discrete tones and silences. Modernism, in its many forms, mirrored the quantum insight, wholeness built from discontinuous parts. The atom's leap became a symbol of creativity itself, the sudden emergence of form from emptiness. As the 1920s unfolded, other physicists expanded Bohr's vision mathematically. Schrödinger's wave mechanics replaced jumps with continuous waves, but when the equations were solved, the results matched Bohr's energy levels exactly. Heisenberg's matrix mechanics described transitions directly, without picturing orbits at all. What had begun as Bohr's daring hypothesis now stood as the foundation of a new science. Yet Bohr continued to defend the necessity of the quantum jump. The mathematics might smooth the process into waves, he argued, but when a photon is emitted or absorbed, the change remains discontinuous. Nature still acts in steps. The wave describes probability. The jump is reality choosing. Heisenberg, inspired by Bohr's mentorship, formulated the uncertainty principle, which gave formal expression to what Bohr had intuited, that it is impossible to know simultaneously both the position and momentum of a particle. This uncertainty was not a defect of measurement, but a feature of existence. The more precisely one property is defined, the less precisely the other can be. Bohr embraced this idea wholeheartedly. It confirmed his belief that stability arises from limitation. The electron's orbit is stable precisely because certain information is undefined. The world endures because it leaves room for ambiguity. These philosophical depths made Bohr both admired and misunderstood. To many he seemed to speak in riddles, turning scientific discussion into metaphysical meditation. But those who worked with him knew that his language mirrored the complexity of the subject. He was not being obscure. He was being exact in a realm where ordinary words failed. How does one describe a jump that occurs outside time as we know it, an event that links the measurable and the unknowable? Bohr found that poetry often served better than equations. He once said that when it comes to atoms, language can only be used as in poetry. His acceptance of that poetic truth allowed him to think freely, to see beyond the boundaries of reason without abandoning rigor. The quantum jump, once a theoretical abstraction, became the foundation of modern technology. The emission and absorption of photons underlie every laser, LED, and transistor. In medical imaging, communication, and computation, Bohr's leap repeats billions of times each second. Each flicker of a screen, each pulse of data, each bit of digital information is a controlled quantum transition. The modern world literally runs on Bohr's discovery. Yet the principle remains as mysterious as ever. Even today, physicists cannot describe the jump in classical terms. It happens outside the continuum of time. Experiments in quantum optics have observed the telltale flashes, confirming that the leap is real, abrupt, precise, and unpredictable. Bohr's intuition endures unchallenged. In his later years, Bohr reflected that the most astonishing feature of the universe is not its complexity, but its coherence. The same rule that governs the smallest atom governs the largest star. Quantum jumps are not confined to electrons. They manifest in every transition of energy, in every change of state. The cosmos, from micro to macro, is a network of leaps, galaxies forming, elements fusing, life emerging. Each event is a quantum transition on a different scale. The stability of the universe is the grand sum of these countless leaps maintaining balance. What seems chaotic is actually choreography. What seems spontaneous is structured. To Bohr, this realization carried a quiet moral lesson. In a world built on discontinuous change, the illusion of permanence must never become complacency. Stability must be renewed constantly through adaptation. Just as electrons maintain their orbits by obeying quantized rules, societies endure by respecting limits while allowing transformation. Progress, like the quantum jump, is not gradual but leaps from one paradigm to another. The challenge is to leap without collapse, to change without losing coherence. In that sense, Bohr's physics became a metaphor for wisdom itself. He conveyed this understanding gently to those around him. When students despaired over contradictions, he would remind them that nature thrives on them. The opposite of a simple truth, he said, is a falsehood. The opposite of a profound truth may well be another profound truth. That aphorism was the essence of the quantum jump. A system can exist in two states that seem mutually exclusive, and yet both are real. The transition between them is not destruction but transformation. The electron does not die. When it leaves one orbit, it is reborn in another. Light itself is the trace of that resurrection. Bohr's thought thus wove physics and philosophy into a single fabric. He saw in quantum jumps the echo of life's own pattern, moments of stillness followed by sudden change, uncertainty leading to renewal, growth, discovery, creativity. All are quantized leaps. Between them lies waiting, potential, the buildup of energy that finally releases as insight or evolution. The atom, endlessly cycling through these transitions, became for him a symbol of hope, a reminder that the universe renews itself through leaps of light. Even after Bohr's death, his interpretation continued to inspire and divide. Some later theories sought to eliminate the idea of the jump, to smooth it into continuous wave evolution. Yet experiments keep reaffirming what Bohr saw so clearly. When a photon is emitted, the change is abrupt. The quantum leap remains at the core of reality. In recent decades, scientists have even managed to observe single electrons making these transitions in real time, watching the atom flicker as it leaps between states, direct visual proof of Bohr's invisible law. The fact that we can now record what he once imagined does not diminish his insight, it confirms it. He had read the code of existence a century before technology could display it. The beauty of Bohr's vision lies in its universality. Whether one speaks of electrons or ideas, stability and change are bound by the same logic. Systems persist by quantizing their transitions, by leaping within limits rather than drifting without bounds. This understanding extends from physics to art, from biology to consciousness. A thought appears not through gradual formation but through a sudden quantum of awareness. Evolution advances through mutations, discrete jumps that redefine life. History itself moves in leaps, revolutions, discoveries, awakenings. The pattern that Bohr uncovered in the atom pulses through every level of reality. When we gaze at a night sky filled with stars, the light reaching our eyes is ancient evidence of quantum jumps that occurred millions of years ago. Each photon began as an electron's leap in some distant atom, traveling across space to tell us that existence endures, that light is the memory of stability through transformation, the message Bohr translated into human understanding. The atom does not fall apart because it is built to leap, and every leap preserves the balance of creation. The same rhythm holds galaxies together and beats quietly in every heartbeat. Bohr once said that physics is not about finding out how nature is, but about what we can say about nature. In that modest sentence lies the humility of a man who saw beyond certainty. He knew that the universe does not yield its secrets to arrogance. The quantum jump was his reminder that truth comes in flashes, brief illuminations separated by darkness, and that stability is the ability to hold faith through the dark between. To explain why atoms don't fall apart, he had to accept that continuity is an illusion, that permanence is a pattern of leaps. That insight remains one of humanity's greatest acts of comprehension. Today, when scientists manipulate quantum bits in computers, when they teleport states across space, when they probe the edges of reality, they are still following the path Bohr began. Each operation, each pulse of energy, each photon emitted or absorbed is a controlled quantum jump, the same act that once astonished a young Dane pondering the hydrogen spectrum. The scale has changed, the principle has not. The stability of information, the coherence of matter, and the persistence of life all rely on the leap. Without it, the universe would fade into uniformity and silence. With it, it sings. And so, in the grand silence of space, the atoms of every star continue their eternal dance, electrons leaping, photons flying, matter renewing itself in flashes of quantized grace. Each jump is a promise that structure will endure, that order will rise again from uncertainty. Bohr's discovery was not merely about atoms, it was about the rhythm of creation. The universe, he taught us, is composed not of continuous lines but of luminous steps. And it is those steps, the quantum jumps, that hold it together. In the quiet dawn of the quantum era, Niels Bohr stood before two worlds that refused to agree. One was the familiar realm of classical physics, ruled by certainty, predictability, and cause and effect. The other was the newborn quantum world, where particles behaved like waves. Motion occurred in sudden leaps, and the very act of observation altered reality itself. Between these two stood a chasm that seemed impossible to bridge, yet Bohr saw a hidden harmony connecting them. He believed that both worlds were true, not in conflict but in complement. His life's work became an attempt to marry the precision of the classical with the mystery of the quantum, to show that they were not enemies but reflections of the same deeper truth. Bohr understood that classical mechanics was not wrong, it was limited. It described the world of everyday experience beautifully, but failed when applied to the subatomic scale. The laws of Newton could predict the trajectory of planets, but not the orbit of electrons. Yet Bohr refused to discard the old for the new. He sought unity, a bridge where both descriptions could coexist within their boundaries. This became the essence of his correspondence principle, the idea that quantum theory must merge smoothly with classical physics where the latter remains valid. It was his way of saying that nature does not contradict herself, she only changes language depending on the scale at which she is observed. In Bohr's view, the quantum world did not abolish classical order, it completed it. The equations of Newton and Maxwell still worked for large systems because, when quantum numbers became enormous, the discontinuous steps of energy blended into the appearance of continuity. The quantum staircase became a classical slope. Thus, classical physics was not overthrown but absorbed as a special case within a larger, subtler reality. Bohr saw this as a profound reconciliation, the universe preserving its consistency even as human understanding expanded. He often said that truth and clarity are not the same. To understand the whole, one must hold contradictions without erasing either side. This marriage between the quantum and the classical was not only mathematical but philosophical. Bohr realized that the observer and the observed could no longer be separated. In the classical world, measurements could be made without altering the system, but in the quantum world, observation itself changed the outcome. The measuring apparatus, built on classical principles, interacted with the atom, forcing it into one of its possible states. The boundary between observer and object, between quantum and classical, was therefore not fixed but contextual. The universe could not be understood from the outside. It was an interaction, a dialogue. Bohr's vision made science not merely a study of things, but of relationships, between scales, between perspectives, between knowledge and mystery. His idea of complementarity grew from this realization. It meant that two seemingly opposite descriptions, wave and particle, certainty and probability, could both be true, depending on how we looked. The universe was not one-sided but dual, and only by accepting both views could we approach completeness. In this, Bohr saw a deep harmony echoing through existence itself. Just as electrons balance attraction and motion to form stable atoms, understanding balances classical and quantum truths to form stable knowledge. The two realms were not different worlds, but different expressions of the same cosmic language, one spoken in the smooth grammar of continuity, the other in the discrete rhythm of quanta. In his lectures and letters, Bohr often likened this balance to the yin and yang of ancient philosophy, light and shadow defining one another, unity emerging from tension. He taught that progress in science comes not from eliminating paradox but from embracing it. The classical and quantum domains, like reason and intuition, sustain each other. Without the predictability of classical law, we could not design experiments. Without the freedom of quantum indeterminacy, creation itself would be impossible. The marriage Bohr envisioned was thus not only scientific but existential, the union of logic and wonder, of what can be measured and what must be imagined. Even today, the structure of this marriage remains the backbone of physics. Every measurement we make begins with a classical device probing a quantum reality. Every theory must reduce to classical results when scaled up. Quantum computers, lasers, and atomic clocks all depend on this unity. The micro and the macro converse constantly, each translating the other's language. Bohr's principle of correspondence ensures that the universe remains consistent from atom to star. His vision of complementarity reminds us that contradiction is not failure but depth. In the end, Bohr's marriage of the quantum and the classical was more than a reconciliation of theories. It was a philosophy of wholeness. He showed that understanding reality requires humility. The truth is not found in one framework alone, but in the harmony between many. The atom and the universe obey the same unseen symphony, each note distinct yet part of the same composition. Bohr's bridge between the two worlds still stands today, reminding humanity that stability, knowledge, and existence itself depend on balance. The timeless dance between certainty and mystery, between the visible and the invisible, between the quantum leap and the classical path that together make the universe whole. When Niels Bohr turned his attention to hydrogen, he was not merely studying an element, he was seeking the key to the universe's architecture. Hydrogen, the simplest atom, held within it the fundamental riddle of existence: why matter is stable, why energy comes in discrete amounts, and why the universe glows in color. Earlier scientists had looked at hydrogen's spectral lines, those bright, precise colors emitted when the atom's electrons shifted states. But no one could explain why they appeared at such exact frequencies. They were like musical notes with no visible instrument. Bohr realized that if he could decode hydrogen's song, he would unlock the language of the atom itself. In 1913 he succeeded, and that success became one of the most beautiful triumphs in the history of science. Bohr began with something daring. He accepted that the electron in a hydrogen atom could orbit the nucleus only in specific, quantized paths, where its angular momentum equaled whole number multiples of Planck's constant divided by 2p. Each orbit represented a stable energy level. When the electron jumped from one level to another, it emitted or absorbed a photon whose energy corresponded exactly to the difference between those two levels. This simple rule explained the entire hydrogen spectrum with stunning accuracy. Each line of color was not random, it was a direct fingerprint of an electron's transition. The mystery of the spectral lines dissolved into harmony. Bohr had discovered that the atom, like a violin, played notes, and those notes were quantized. The beauty of this revelation was that it united theory and observation in a single stroke. For years, experimenters had measured hydrogen's spectral lines and arranged them into mathematical patterns known as the Balmer series. Bohr's equations predicted those same values precisely, providing the missing foundation that connected experiment to principle. Suddenly, light, energy, and structure all spoke the same language. The atom was no longer chaos, it was order built from quanta. The faint glow of hydrogen in a laboratory became a window into the deepest laws of creation. Every photon emitted was the record of a cosmic rhythm, an electron falling home, releasing light as it settled into peace. Bohr's model not only explained hydrogen but also laid the groundwork for understanding all atoms. It revealed that every element's chemical behavior depended on the arrangement of its electrons in quantized shells. Hydrogen, with one electron, was the simplest symphony, but its pattern echoed through all matter: helium, lithium, carbon. Each followed the same quantized logic, differing only in complexity. The entire periodic table was suddenly illuminated by Bohr's idea. Chemistry became a branch of quantum physics. The bonds between atoms were nothing less than shared quantum states. The ordinary world, the air we breathe, the water we drink, the blood in our veins, existed because electrons occupied specific, quantized orbits instead of collapsing into the nucleus. Bohr had shown not just why atoms don't fall apart, but why they come together. This triumph carried with it a quiet elegance that captured the imagination of an entire generation. The atom was no longer invisible chaos, it was a structure of exquisite simplicity. Hydrogen's single electron moved in silence around its nucleus, yet from that motion came all light and color. Bohr's equations told a story of balance. Centripetal force pulling the electron inward, centrifugal motion pushing it outward. The two held in perfect quantum harmony. This balance produced the world's most fundamental stability. To Bohr, hydrogen was not just matter, it was a microcosm of the universe, a reminder that simplicity could contain infinity. But Bohr's discovery also carried a deeper philosophical meaning. The quantized nature of hydrogen revealed that nature herself had boundaries, that even at the smallest scales freedom existed within limits. Energy was not continuous, it was counted, measured, and exact. The universe, for all its vastness, operated through small, indivisible steps. This discreteness, once thought impossible, was the secret of its endurance. If electrons could move freely, they would radiate energy endlessly and spiral into collapse. Instead, quantization confined them to stable levels. Stability, Bohr realized, was the result of nature's discipline. The invisible mathematics that governed every act of creation. When Bohr's paper appeared, the scientific world stood in awe. Einstein himself praised it, calling it astonishingly beautiful. The simplicity of hydrogen's explanation hinted at a unity behind all things. The light from distant stars, analyzed through spectroscopy, showed the same lines Bohr had described. It meant that hydrogen in a laboratory on Earth and hydrogen in a star billions of miles away obeyed the same law. The universe was consistent, connected by quantized order. In Bohr's theory, the cosmos had found its common rhythm, yet Bohr remained humble. He knew that his model was only the beginning, a bridge between classical and quantum realities. Later theories by Schrödinger and Heisenberg would refine his picture, replacing orbits with waves and probabilities. But the heart of the idea, discrete energy levels, would remain untouched. The hydrogen atom was a truth that survived every revolution that followed. It became the foundation of modern quantum mechanics and the cornerstone of atomic physics. Every laser, every solar cell, every quantum device in the modern world owes its existence to the mathematics that Bohr derived from the simplest of atoms. Even more profoundly, Bohr's hydrogen model reminded humanity of its place in the grand design. The same principles that governed an electron's motion governed the stars themselves. Energy flowed in steps. Light was born in transitions. The universe was built not from chaos but from rhythm, not from infinite continua but from measured harmony. Hydrogen, abundant, elemental, humble, became the proof that the laws of the cosmos are written in simplicity. Bohr revealed that at the foundation of all complexity lies an atom whose single electron dances to the beat of quantum law, and in that dance resides the secret of existence. Niels Bohr was not content with merely explaining how atoms stayed together. He wanted to understand what their strange behavior revealed about reality itself. From the equations and experiments, he saw that matter behaved in ways that could not be captured by the rigid logic of classical thought. Electrons were both particles and waves. Light could act as matter, and matter could act as light. Observing an experiment changed its outcome. These contradictions were not errors, but truths seen from different angles. Bohr realized that to understand the quantum world, humanity would have to think in a new way. From this realization was born his greatest philosophical contribution, the principle of complementarity, the idea that two seemingly opposite descriptions of nature can both be true, depending on how we look at them. This principle did not emerge from speculation. It arose naturally from Bohr's struggle to interpret the results of quantum experiments. He saw that physics had reached a point where the old language of certainty no longer worked. When light was measured one way, it behaved like a wave. When measured another way, it behaved like a particle. Both observations were correct, yet they could not be combined into one picture. Instead of choosing between them, Bohr proposed that reality itself is built from such dualities. The electron is not sometimes a wave and sometimes a particle, it is both, but never simultaneously in the same sense. Each description complements the other. Together they reveal more than either could alone. Bohr's idea went beyond physics. It was a new way of seeing truth, not as a single exclusive statement, but as a harmony of opposites. He believed that knowledge grows not by eliminating contradictions but by holding them in balance. Nature, he said, does not fit neatly into the boxes our minds create. What we call paradox is often a sign that we are touching a deeper layer of reality. The world of the atom, with its dual behavior, was teaching humanity that understanding must evolve along with observation. In this sense, the atom became a mirror of human thought itself. Mysterious, layered, and complete, only when viewed from multiple sides. In Bohr's vision, complementarity explained not just light and electrons, but the entire relationship between the quantum and classical worlds. On the quantum scale, reality existed as potential, a spectrum of possibilities described by waves of probability. When measured with classical instruments, that potential collapsed into concrete outcomes. The active observation selected one face of reality and concealed the others. Both aspects were necessary. The quantum provided freedom, the classical provided form. One could not exist meaningfully without the other. This balance between possibility and certainty became, for Bohr, the essence of existence. He extended the principle to philosophy, biology, and even psychology. Just as an electron's dual nature required complementary views, so did life and consciousness, thought and emotion, logic and intuition. Individual and collective, each defined the other. To Bohr, this was not mysticism but realism. The world is built from relationships, not isolated facts. Every truth casts a shadow, every perspective reveals one side while hiding another. In the quantum realm, this was measurable. In the human realm, it was lived experience. Bohr saw the unity of both. His colleagues were sometimes frustrated by his insistence on paradox. They wanted clarity, Bohr offered depth, but history would prove him right. Complementarity became the guiding philosophy of quantum mechanics. It explained why different mathematical formulations, wave mechanics, matrix mechanics, path integrals, all described the same phenomena from distinct angles. Each was incomplete alone but complete together. Reality itself was complementary, layered, multidimensional. This way of thinking also transformed the way humanity approached knowledge. Science, long seen as the conquest of uncertainty, became instead a dialogue with it. Bohr taught that understanding does not destroy mystery, it refines it. The closer we look, the more we realize that opposites coexist. The atom, far from being a simple particle, was a theater of dualities. Stability born from motion, continuity built from discontinuity, certainty emerging from chance. Complementarity was not a retreat from logic but its expansion, a recognition that truth is bigger than language. In his later years, Bohr often reflected on the moral implications of his principle. If opposites can be true in nature, then perhaps harmony in human affairs also depends on accepting duality, nations and ideologies, reason and faith, freedom and responsibility. The balance that sustains the atom might also sustain civilization. For Bohr, science was a path not just to knowledge but to wisdom, a guide to coexistence in a universe that thrives on unity through difference. Even today, the principle of complementarity stands as one of the deepest insights into the structure of reality. It reminds us that understanding comes not from choosing sides, but from integrating them. The electron's mystery becomes our own. We are particles when we act, waves when we imagine, both bound and free, measurable and infinite. Bohr's philosophy transformed the atom into a symbol of truth itself, stable, paradoxical, and luminous. He showed that the universe does not demand certainty from us, only openness, the courage to hold contradictions until they reveal their harmony. And in that harmony, he found the true meaning of knowledge, not the elimination of mystery, but the realization that mystery and understanding are complementary parts of the same eternal light. Niels Bohr's legacy was far greater than a scientific theory. It was a revolution in how humanity understands existence. His discovery that atoms remain stable because of quantized energy levels was only the beginning. What followed was a transformation that reached across physics, philosophy, and human thought. The concept that the universe is structured by invisible rules of probability, rather than mechanical certainty, opened the door to a new worldview. Bohr's work became the foundation upon which modern quantum mechanics was built, inspiring an entire generation of scientists, Heisenberg, Schrödinger, Dirac, and beyond, to explore a realm where matter and mind, observation and existence intertwined. His ideas became the seed from which the quantum revolution grew, changing not only science but the way humanity perceives reality itself. The early decades of the 20th century were marked by profound shifts. Einstein had altered time and space, but Bohr redefined the atom, and with it the very notion of matter. He taught that stability itself is not static but dynamic, that the universe sustains itself through quantized balance. Atoms, once imagined as solid and unchanging, became living systems, pulsating, leaping, radiating energy. From Bohr's vision emerged the understanding that every object, from a grain of sand to a star, is made of the same quantum architecture. The building blocks of creation followed the same laws everywhere. Electrons orbiting in harmony, photons carrying energy across the void, probability giving birth to form. This realization unified the cosmos. What happened inside a single atom also happened inside the heart of a star. The micro and the macro were mirrors of the same design. The Bohr model became the cornerstone upon which future discoveries stood. It was not perfect. Later theories would replace his orbits with wave functions and uncertainty, but its spirit remained embedded in all that followed. Heisenberg's uncertainty principle, Schrödinger's wave equation, Dirac's quantum field theory, and even Feynman's path integrals all grew from the soil Bohr had prepared. His model gave science a language for the invisible, a way to describe the unpredictable dance of particles that make up reality. What Bohr had begun as an explanation for why atoms do not collapse became the gateway to understanding why anything exists at all. Beyond physics, Bohr's influence reached deep into philosophy. His idea of complementarity, that opposites can both be true depending on context, reshaped human thought. It taught that knowledge is never complete, that understanding comes through paradox and dialogue. In a universe built on quantum uncertainty, humility became a scientific necessity. Bohr's philosophy turned science into an act of coexistence with nature rather than domination over it. He saw the scientist not as a master of the world but as a participant in its mystery. Each observation, he said, is an interaction, a moment where the observer and the observed become one. The universe, in his view, was not a machine to be dissected, but a conversation to be understood. Bohr's legacy also lived on through his students and collaborators, many of whom went on to shape the 20th century. Werner Heisenberg, who developed quantum mechanics, always described Bohr as the guiding light of his ideas. Einstein and Bohr debated endlessly, one defending determinism, the other embracing probability, yet both knew they were exploring the same truth from different sides. Their debates became a theater of thought that defined the boundaries of modern science. Even in disagreement, Bohr inspired respect because he never sought victory, only understanding. He once said that the goal of argument is not to prove who is right, but to reach the truth that lies between. That humility became his most enduring mark. As decades passed, Bohr's insights found expression in every branch of modern life. The quantum revolution birthed technologies that reshaped civilization: transistors, lasers, semiconductors, quantum computers. The energy within atoms became both a source of power and a reminder of responsibility. Bohr himself lived long enough to see the destructive potential of his ideas in nuclear weapons, and he dedicated his later years to promoting peace and the responsible use of science. For him, understanding the atom was not enough. Humanity had to understand itself. The same discipline that governed electrons, balance within boundaries, should guide nations and minds. In his view, complementarity was not just a law of nature, but a moral principle. Opposites could coexist without annihilation if they recognized their mutual dependence. Even after his death in 1962, Bohr's vision continued to illuminate the path of discovery. Quantum theory evolved, but the spirit of his thought remained untouched. The world of modern physics, from quantum field theory to cosmology, still rests on his foundation. When scientists describe how particles emerge from fields, how matter and energy convert, or how the universe evolved from a quantum fluctuation, they are walking in the light that Bohr first lit. He showed that behind the apparent randomness of existence lies structure, behind uncertainty lies order. He transformed chaos into coherence, making the incomprehensible visible through logic and humility. Yet perhaps Bohr's greatest legacy lies not in equations but in perspective. He taught that the purpose of science is not to remove mystery, but to deepen our appreciation of it. The universe, he said, is not absurd. It is subtle beyond understanding. His work turned the atom into a symbol of harmony, a miniature cosmos where contradictions coexist peacefully, where light and matter exchange energy in perfect rhythm. The stability of atoms became a metaphor for the stability of life itself, fragile yet enduring, chaotic yet ordered, finite yet infinite in depth. Today, when scientists manipulate quantum bits in laboratories, when engineers harness atomic energy, or when philosophers ponder the limits of knowledge, Bohr's spirit remains present. His equations describe the microscopic world, but his wisdom describes the human one. He showed that truth has many faces, and that the task of understanding is never complete. The atom's endurance is our endurance, its structure our reflection. Through Bohr, humanity learned that existence is not built upon certainty but upon harmony, the delicate balance between the measurable and the mysterious. His legacy is not confined to textbooks. It lives in every light that shines, every thought that questions, and every moment that reminds us that even in uncertainty, the universe holds together with unbreakable grace.